Thank you very much for inviting me in this very special conference and workshop. Actually, I'm not very well today, so I'll be a bit brief. Actually, as far as my research is concerned, I'm mainly working in two areas. One is a very emerging paradigm, which is quantum-like modeling in decision science, and then applications to finance and other areas, which is like my main work. And then along with this, I'm also working in quantum foundations, which is more into quantum physics and philosophy of science. So here I'll be very briefly talking about quantum-like modeling in decision science and applications in finance. There are various interesting things which are happening in this field, quite a versatile field. For example, quantum games and financial market modeling, which I have been working with my co-authors earlier. Though in this particular presentation, I would be mainly presenting a general framework, but if more concrete papers or more concrete models you are interested in, then I'd refer to some of my recent works with Polina Krenikova, 2019. Incidentally, Polina is also from Leicester University. So there we applied one particular quantum finance model in asset trading. That is these investors' diversity of opinion in that kind of an area. Then along with Professor Patra, who is a very renowned quantum physicist, we are working on some of the game theoretic papers, etc. So I'm really based at OP Jindal Global University currently, and we also have a center at OP Jindal University, which is CEASP, mainly working in complexity economics. I found that some of the papers presented earlier also related to networks and complexity modeling. So it would be of great interest to us also to kind of network more in these areas. Now, very briefly saying, what is quantum-like modeling? Now, there are a couple of things here. The first thing is that the qualifier like is quite important because this simply means that it is not suggested here that there is a genuine quantum physical model of human brains, though that itself is a very maybe a viable project. Many brilliant scientists are working in that area. But we are rather much more pragmatic. What we would like to do is basically to use various interesting mathematical frameworks which have been used quite widely in quantum physics and quantum field theory mainly, and to see that whether they can throw some new light into cognition modeling and its applications in financial markets and so on. So there's a huge empirical evidence from cognitive science about limitations of Boolean logical framework to describe decision making in general. For example, we know that standard decision theory is very much based on set theoretic setups and from probabilistic modeling. We can think about Kolmogorov decision-making theory or measured theory. However, it has also been shown since the late 60s and 70s itself that when real agents in, say, financial market situations or in rather controlled atmosphere, they really do choices mainly under ambiguity and uncertainty, then there are a lot of so-called paradoxes or so-called anomalies which arise, which cannot be satisfactorily described within the framework of, say, neoclassical decision theory or utility maximization theory, to give a very oversimplistic name. For example, question order effects and failure of sure thing principle, conjunction fallacy, some of which I will refer to again. These kind of anomalies do appear, and one standard way to address these anomalies would be to take the behavioral finance or behavioral economics route and then try to either suggest that human beings most of the times may not be fully rational. There is bounded rationality models also, or for example, to use various kind of heuristics and thumb rules There's a huge literature of behavioral finance, we know, but we are not, in a way, against behavioral finance literature. Certainly, that has informed us a lot. But along with this, we'd also like to remind that there can be a better, perhaps, a mathematical framework which would be able to retain most of the standard results of decision theory, but along with this, also try to describe various so-called anomalies in a more normal way, so that we don't really need to think that these are some pathological cases or these are some like kind of irrational behavior altogether. So that is basically what quantum-like modeling would like to do, borrowing the language of quantum computation and quantum information theory. Later, I will also try to argue that there are other ways of introducing quantum computation in finance too, but this is a decision theoretic perspective. There are various other perspectives also. One very important and central notion in all of our modeling and mainly in decision theory is the contextuality thing. That is, whatever decision making we can think about. For example, some of the papers I was also going through in this great workshop, maybe contextuality can have a very important role to play in the final choice making or final asset allocations, for example, and so on. So the context in which the decisions are made has a direct impact in the ultimate results, and whether that can be satisfactorily modeled with the help of a probabilistic modeling. So that is like one of the central tenet of quantum-like modeling. But definitely here also we have to be careful that we are not talking about quantization. So quantization is the central feature of quantum physics, which is like reflected in quanta of least action or Planck's constant that we do not need. So we have to be careful to build up that kind of an algebra or that kind of a mathematical model, which would have contextuality and all the other desired features, but not directly going into some more hardcore physics fact of it. Quantum-like modeling, which I have abbreviated here as QLM, is a comprehensive decision-making paradigm. There have been many pioneers in this field. Immanuel Haven and Andrei Krenikov came out with a seminal textbook in 2013, and then Yukalov and Sornetti, they have been very much active in something known as quantum decision theory, where the dynamics of decision-making model comes in. Buzemeyer et al. From Indiana University, Bloomington, and others, they are a very strong group of cognitive modelers, and so on. Now, here in our specific model, or our specific framework that we are adhering to, we see that this contextuality is actually the central tenet of our modeling. And here there are quite a few choices that how to model contextuality in a decision framework. Two most important choices are, one, it goes back to Niels Bohr, one of the founding fathers of quantum mechanics, Copenhagenish interpretation. So Bohr adopted the stance that the state of measuring device and the state of the object cannot be separated from each other during a measurement and constitute a dynamic whole. And that is what is actually thought as to be contextuality in that particular paradigm. So it's a kind of like an unanalyzable or unseparable whole between the decision maker, for example, in our case, the mental state of the decision maker, and say the information environment. Now, there have been some recent works in that particular area to give a more mathematical framework. We have given one of them, which I will go through. There are other definitions of contextuality also. For example, joint measurement contextuality, or JMC. That is basically focused on kind of joint probability distributions of random variables. Then certainly there are interesting conditions to be met to see that whether the data with which we are working, choice data, for example, they really reflect contextuality or not. One particular condition is often called as no signaling condition. That these are some interesting kind of like summation forms which have to be made. And then after that, we can look for whether there are further violations of inequalities, like Bell inequalities or CHSH inequalities are quite well known in this particular literature. And
So, Sudip, can I just sort of jump in there? Just from a layperson point of view about quantum physics and so on. How would it just give us a very simple example of, say, we are all familiar with state preference models. Let's say there are two states, a probability, and the sum of probabilities add up to 1. How would that simple framework be made into a quantum physics framework?
Yeah, I just have it. I mean, just in the next slide.
Okay, thank you.
Yeah. So basically what we have here is we can straight away go to this particular feature, or maybe even this particular slide. So in our modeling, what we do basically, we start with a particular cognitive state or a belief state of an individual or of a decision maker. And this particular belief state is thought as to be a kind of like a ray in the complex linear vector space, which is the Hilbert space. So Hilbert space is our like state space, if you want to say in that way. And then certainly that particular state is represented with the help of certain linear combinations of basis states, which I will get back to. Say, for example, you have two bases, 0 and 1. So 0 may be like kind of like a yes state for the mental state, and 1 may be a kind of like no state for the mental state. And then you have a linear combination of 0 and 1, which actually would describe the ray in the Hilbert space to start with. That is like the basic mental representation of the state. Now, these coefficients of these particular linear combinations are often called as to be probability amplitudes. Now, these probability amplitudes are not exactly equal to the classical probabilities, but it is only when you make a measurement on that particular state that which particular final choice that individual would make, that whether either go for yes state or a no state, like updation of mental state, then only those probabilities would be kind of materialized. So what you do is basically you square the amplitudes in that linear superposition description, and the square of the amplitudes actually becomes your classical probability. So this is like basically a correspondence between the quantum-like description of the mental state or cognitive state and the classical probabilities. Now, in that particular picture, geometric picture, the most important thing that we have is that while you calculate the probabilities of a particular event happening, for example, or for a particular choice to take place, for example, like in this particular formula, probability of A happening, which is a conditioned to another particular event of B, and B is taking either of these values B1 and B2, then in this formula for total probability, as we say, you have some extra interference terms coming up. And these interference terms, which I have just written in red here, these are the interesting terms which comes up in the this quantum probabilistic framework. And the claim, as far as it goes, of different papers is that these deviations that we observe in reality from the classical predictions, as I was talking about earlier, the anomalies, for example, they can be described by suitable choice of the interference terms. There is a huge amount of research which has gone into this particular area. There are different types of interference terms, hyperbolic as well as trigonometric interference terms. The main purpose is to show that how the deviations occur. For example, one particular example, which is quite well studied nowadays, is the prisoner's dilemma example in real life. So we know that in a typical rational framework, we have only one non-cooperative equilibrium, defection equilibrium in the first round of the game. until and unless the game is repeated infinitely and so on. But in real life scenarios, what happens is that under uncertainty and ambiguous scenarios, people really do not always adhere to that kind of Nash equilibrium prediction. And there are different types of behavior which is coming up. So those different behaviors, the probability of like deviating from that stubborn Nash equilibrium can actually be shown to follow this kind of interference term patterns, which are capturing the deviations from the equilibrium behavior. Now going back to our own.
Sorry, can I just ask you a little more about the interference factors? What is bringing that about? It's not random white noise, is it?
Yeah. So say, for example, interference pattern, actually the name comes from, it has a physics background, but we don't have to get too much into it. The main thing here is that these are deviations from the classical results of total probability. So if you calculate the total probability with the help of, say, any kind of a simple Boolean logical framework, you do not get these interference terms. So these interference terms are like some kind of perturbative terms that you get in your results. Now, so going back to our own mathematical framework, then what we can do is basically we can start with this particular state of cognition, and we call it as psi. And then we have like two indexes here, or we can say two parameters. One is C and one is Q. C is the context in which the decision making is happening, and Q actually denotes the questions which are asked to the agents. Now, if this is the mental state, and this particular state is then, one can say, modeled as a ray in the complex linear vector space, which is the Hilbert space. Now, the answers to this particular questions, or say the response or to this particular mental state when it is perturbed or when it is kind of asked any question, is given by random variables. So this RCQ, these are like the responses to the questions. And again, two indexes, so C for context and Q for the questions. If C and C prime are incompatible, one has complementarity. Complementarity means that there are different mental states which are corresponding to different contexts, which may not be compatible with each other all the time. So they cannot be observed at the same time. These incompatibility is also to be understood in the sense of mutual exclusive context, like in the quantum double slit experiment where one or both slits are open, they cannot coexist with each other. So these are like different kind of exclusive contexts. So we can, in a way, give this representation of mental states in exclusive context. And therefore, one can go on in this way and show that, say that like this kind of context, like if C is like Alice ate a banana and then C prime is like Alice ate an apple. So these are like two incompatible contexts with each other. We cannot like have both at the same time, and they can be represented by these two different mental states, psi CQ and psi C prime Q, which are not equal to each other, and therefore the responses to these two states would also be different, RCQ and RC prime Q, which are not equal to each other. Now, to represent this thing, we do not really need to get back to non-commutating operators and so on, which some models might have done earlier. But right now, we can show that it can be done in a much more simpler way, not really going into non-commutation algebra. Because if we go into non-commutation algebra to represent this, then we get into the representation of, Planck's constant, etc., which is not required in decision science. This is one particular example which I was saying. Now, the basic mathematical model is that we have a...
Sudip, you have another 5 minutes, actually less than that. So If you can wrap up within 5 minutes, it would be good.
Okay.
Yeah,
Sure. Okay, so basically the representation of this whole mathematical structure comes from, first of all, doing two things. First of all, to choose the basis in which the state has to be written down. Say one particular basis would be a computational basis, like the 0 and 1. And here is where the language of quantum computation also comes in. So 0 is again represented by 1, 0 column matrix and 1 by 0, 1 column matrix. And then we have this psi state, which can be represented in this way. Say, for example, cos theta ket 0 plus e to the I phi sine theta ket 1 with some suitable range of theta and phi. Theta and phi being the polar and the azimuthal angle on a unit sphere, which is often known as the Patra sphere. And then what you can do is that you can keep on changing the theta and phi. So these are the two parameters which you can keep on changing, and that will show that how the mental state that you are representing on the unit sphere, that keeps on changing over. So and then also you have Q. Q means the different questions. So if different questions also keeps on changing, the mental state also changes. This is one particular example of Patra sphere. Now, the other thing that you can do always is that you can also change the context. So either you can change C or Q. So changing of the context will definitely mean that you are choosing a different basis. So rather than 0 and 1 basis, you are choosing something like a really linear combination of 0 and 1 and so on. That would change the mental state from CQ to C prime Q, for example. So these are different flexibility you have in this particular model. Now, apart from this, you can also keep on kind of give more and more general representation of the state, which is often called as density matrix representation. I won't be going too much into that. There's like direct products of kind of this psi CQ representation. This actually gives us much more flexibility in introducing noise in the data also. For example, we know that in decision making, often there is a noise in choice. The last part of the whole thing would be like to construct suitable probability measures, how to calculate the probabilities in this whole paradigm. There are two things here. The first thing is like for the updation of the state. And the second thing is that actual calculation of the probabilities. That is actually done with the help of something known as to be POVMs, which are known as positive operator value measures. Due to brevity of time, perhaps I won't be able to go into that. But this is basically how this density matrix state rho is updated from one state to another state. Say, for example, when new questions come in or new interaction comes in the atmosphere, the mental state keeps on updating and so on. And you have a nice formula for calculating the end choice that is given by this trace formula of the projector multiplied by the density matrix. Projector means say in this case simply the positive operator, which takes you to that particular one single choice like yes or no.
Sudip, you probably only have about 30 seconds left.
Yeah, so basically I would just like to end here that this particular paradigm is actually going into a lot of areas, like one is like finance very much, which definitely we can talk a lot later on, that there are different types of tools which can be used in finance, like operator approach, ladder operators and path integrals, etc., which can be taken from this language. And it has been shown very recently that a lot of interesting problems can be studied. I'd just like to end on one particular problem, which has been talked about quite a lot, that is common knowledge formation. We know that in neoclassical economics also common knowledge plays a very important role in theoretical modeling. Now, if the agents do follow a different kind of logic rather than the standard Boolean logic, then it can be shown that the common knowledge theorem of Robert Aumann, for example, that can be relaxed. And there are like different solutions coming up rather than the standard solution of not possible to agree to disagree. And we know that in financial markets, there's a lot of situations where divergence of opinions are rather more important rather than convergence of opinion. So in these areas also, this kind of mathematical modeling can really help us. And then certainly there is also an empirical part to it, which I'd be very happy to discuss later on. But this is a very brief overview, I should say. Thank you.
Great. Thank you. Are there any questions? Yes, Ankur.
Hi, Sudip. So I have a question regarding this particular modeling paradigm. I'm of course new to it. I have very little idea about it, but I was just wondering that how close does it come to some of the other decision modeling paradigms like fuzzy logic and all? Because a number of terminologies that you were using, for instance, when you were talking about Boolean logic, not following a Boolean logic, or maybe impreciseness of information and stuff like that. A lot of these kind of things are spoken about by experts working in the area of fuzzy logic as well. And at the same time, there is a lot of mathematicians who criticize people working in the area of fuzzy logic by saying that, okay, whatever these people are talking about can very well be done with just probabilities. So what is your take on that, and how close this particular area comes to maybe some of these other paradigms that people are looking at? And of course, the other thing that I observed was that you're taking some sort of a function of probability as well, right? In one of the equations I saw, there was some function of probability with interference and those sort of things. And there it comes very close to maybe other sort of techniques like prospect theory as well, where you take a function of probability and then you create the utilities and everything out of it.
Yeah, yes, I think that these are very, very interesting questions. And I will say that there are a lot of interfaces. There is no doubt about that, that there's some kind of commonalities also one can observe. But quantum-like modeling as of now is rather quite apt in kind of working with the real data also. And also, I will say that the deeper questions, for example, the question of contextuality, that can be in a way modeled better with the help of this quantum-like modeling, because it also has a very solid theoretical perspective to how to form your approach towards contextuality and others. And definitely there are different ways of introducing. So I have just given one particular representation. There are other ways of representing quantum-like modeling too. And also one important area which definitely I didn't get time to get into is basically the game theoretic part of it. There is a very good amount of research happening in using this framework in understanding and designing real games. So this is perhaps one way in which it is a bit different from the other paradigms, where we can really design real games with the help of, say, the quantum computation, if you like to say. And one of the aims of designing these games have been to generate superior strategies, or say superior equilibrium outcomes. Like one very important game which has been studied is Prisoner's Dilemma. And I think that from the late 90s, maybe 1999 or something, there have been very interesting protocols which have been designed by mathematicians, where using certain interesting features like entanglement in a particular system, you can generate superior equilibrium outcomes. So these are some of the advantages that you can have with this framework.